A cosmic signal flashes with the power of 500 million suns and then disappears forever. This is the mystery of fast radio bursts, or FRB, brief radio whispers from galaxies billions of light years away. By the end of this, you will understand how these fleeting pulses are reshaping our very picture of the universe. We will uncover why some of these bursts repeat while others vanish without a trace, and we will explore the startling possibility that they might not be natural at all. What do you believe is waiting for us in the cosmic dark? Buried in old data, a cosmic secret was waiting to be found. It was 2007, and astronomer Duncan Lorimer, working with his student David Narkevic, was not looking for a mystery. They were engaged in the meticulous work of cataloging pulsars, using archived observations from the Parkes Radio Telescope in Australia. But then they saw it. A spike of energy so powerful, so fleeting, it was almost dismissed as noise. This signal, a blast of radio waves that lasted for a mere 5 milliseconds, had the raw power of 500 million suns. It had been sitting in the data for years, completely overlooked. Today, we know it as the Lorimer burst, the very first documented fast radio burst. Its arrival was met with profound skepticism. Could it have been a glitch from a passing satellite? Perhaps terrestrial interference from someone's microwave oven on the observatory grounds. The signal's most telling clue, however, was something called its dispersion measure. This is a kind of cosmic fingerprint, a way to measure how much material the radio waves had to travel through. The higher the dispersion, the farther the waves have journeyed. The Lorimer burst's dispersion was immense, far too high to have come from within our own galaxy. It pointed to a source billions of light years away, a truly extragalactic origin. This single 5-millisecond blip shattered our assumptions. It proved that the universe was broadcasting incredibly powerful, invisible messages, and we had only just learned how to listen. The hunt for more of these cosmic ghosts was now on, but the question remained: what in the vast darkness was capable of such a shout? So what does this ghostly signal actually look like? Think of a fast radio burst as the universe's most powerful camera flash. It goes off for just a few thousandths of a second, a blink so fast you would miss it if you blinked yourself. Yet in that instant it can outshine 500 million suns. This is not a steady beacon like a lighthouse. It is a single, spectacular flash of radio light, and then, for most of them, absolute silence. The key to understanding their epic journey lies in a subtle distortion of the signal itself. When an FRB travels across the universe, its light does not arrive all at once. The higher-pitched radio frequencies get here first, while the lower, deeper tones trickle in a few moments later. This effect is called dispersion. It is the same reason you see a prism split white light into a rainbow, but here the prism is the thin, invisible gas that floats between galaxies. The more stretched out the signal is, the more stuff it has traveled through and the farther it has come. This is how we know these bursts are not local. Their immense dispersion measure points to origins billions of light years away. In galaxies so distant their light is just a faint whisper. This makes the underlying mystery even more profound. What kind of cosmic engine can concentrate the energy of a star's entire lifetime into a pulse that lasts less than a heartbeat? And why do most of these flashes happen only once, while a select few stubbornly, mysteriously repeat? That single photon of radio light begins its journey not in emptiness, but in a storm of unimaginable violence. It races away from its source, a cosmic event so powerful it can outshine a galaxy. For billions of years, this tiny messenger travels through a universe that is far from empty. It plunges through vast, invisible clouds of ionized gas, the sparse plasma that floats in the immense voids between galaxies. Each encounter with an electron in this plasma acts like a tiny speed bump, slowing the light down just a fraction. But crucially, it slows the lower frequency waves more than the higher ones. This is what creates that stretched descending chirp that astronomers see. The more the signal is stretched, the more of this invisible, scattered material it has traveled through, giving us a direct measure of the cosmic distance it has crossed. This journey is not a straight line. The photon's path is warped by the gravity of all the matter it passes, both seen and unseen. Dark matter, the invisible scaffolding of the cosmos, bends the fabric of space-time, subtly steering the signal on its multi-billion-year voyage. When this faint echo of a cataclysm finally reaches Earth, it is astonishingly weak. That initial blast with the power of 500 million suns has been diluted by its epic trek across the cosmos. By the time it washes over our planet, its energy is less than what you would use to lift a grain of sand. Capturing this whisper requires the immense, silent dishes of the world's greatest radio telescopes, listening patiently for a flash that lasts less than the blink of an eye. Each burst is therefore a time capsule and a cartographer. It carries within its distorted waveform a coded map of the cosmic web it has traversed, revealing the distribution of the universe's most elusive material. We are not just detecting a flash, we are reading a diary of a journey across space and time. This single, fleeting flash was thought to be the final word, the last cry of a cosmic object destroying itself. But the universe had a surprise in store. In 2016, everything changed with a single designation, FRB 1211-2. This was not a one-time event. It was a source that spoke, fell silent, and then spoke again hundreds of times over. It was the first confirmed repeater, and its discovery shattered the neat idea that all fast radio bursts were born from a single, catastrophic end. Suddenly, astronomers had to confront a new reality. There were two distinct classes of these signals, the one-offs and the great repeaters. This is a fundamental dichotomy at the heart of the mystery. It suggests that the cosmos might be using two completely different engines to produce these incredible flashes of energy. The one-time bursts fit the picture of a final, violent act. Imagine two ultra-dense neutron stars, the corpses of dead suns, locked in a final, spiraling dance until they collide and merge in a spectacular explosion. That event could unleash a titanic shockwave, producing a single, brilliant radio burst as its final signature. Or perhaps it is the collapse of a supermassive star into a black hole, a cataclysm that literally tears a star apart from the inside out. These are events of pure destruction, which is why the signal never comes again. But the repeaters tell a different story. They point to a source that can survive its own outburst. The leading suspect is a magnetar, a special type of neutron star with a magnetic field so intense it could erase your credit card from 500,000 light-years away. These young, hyperactive stellar corpses are known for violent starquakes and immense magnetic eruptions. A crack in the magnetar's rigid crust could release a shattering blast of energy, and since the star remains intact, it could easily do it again and again. The repeater's stubborn persistence is a gift to science. Because it keeps flashing, astronomers can train other telescopes on its location, leading them directly to its home, a small, turbulent dwarf galaxy 3 billion light-years away. This ability to pinpoint the source and study its environment is nearly impossible with the one-off bursts, which vanish as quickly as they appear. So the Great Divide is not just a curiosity. It is a crucial guide, forcing us to ask if we are hearing the last scream of dying stars or the tantrums of infant stellar magnets. The answer could reveal two entirely different chapters in the life and death of stars. The repeating signals found their first real suspect in the fury of a magnetar. Imagine the crushed core of a dead star, a city-sized object with a mass greater than our sun, spinning faster than a kitchen blender and wrapped in a magnetic field of almost unimaginable strength. This field is trillions of times more powerful than Earth's, a force so intense it could warp the very atoms in your body from thousands of light years away. These magnetars are cosmic pressure cookers, and their rigid crusts are under constant, unimaginable strain from the magnetic fury within. Occasionally, that crust can no longer hold. It cracks. This event, a starquake, is like a tectonic shift on a neutron star, and it unleashes a cataclysmic flare of pent-up magnetic energy in a fraction of a second. The theory that such an eruption could power a fast radio burst had been circulating for years, but it needed proof. Then, in April 2020, a magnetar right here in our own Milky Way galaxy, known as SGR 1935+2154, finally spoke up. It let out a brilliant radio burst. While its energy was thousands of times weaker than the extragalactic FRBs that travel from distant galaxies, its profile was a perfect match. It was the smoking gun, the first tangible link between a known celestial object and an FRB-like event. This single observation from our galactic backyard transformed the magnetar from a speculative idea into a leading contender. Theorists quickly realized that if a relatively old, quiet magnetar in our galaxy could produce such a flash, then a younger, far more hyperactive magnetar in a distant, star-forming galaxy could easily generate the full, staggering power of an extragalactic FRB. This model elegantly solves the puzzle of the repeaters. A magnetar does not destroy itself in a single outburst. It can survive its own violent starquakes, only to build up pressure and crack again weeks, months, or years later, sending another coordinated shout across the cosmos. While not every single one-off burst may fit this picture, the magnetar provides a solid, physically plausible anchor for at least a significant fraction of these cosmic mysteries. It is a known monster capable of the very violence we have been detecting from the depths of space. But what of the flashes that never return? Their silence is as meaningful as the repeater's chatter. For the one-off bursts, the single, definitive shout, astronomers suspect a far more final kind of violence. These are the cosmic cataclysms, events where the source is not just damaged but utterly destroyed. The leading scenario is a merger of unimaginable density. Picture two neutron stars, each one the compressed core of a dead star, locked in a gravitational embrace for eons. They spiral inward closer and closer until they finally collide. This collision is one of the most energetic events in the universe, known to produce a short gamma-ray burst, a flash of high-energy light. Theorists suggest that in the chaotic aftermath of such a merger, as immense magnetic fields are twisted and amplified, a colossal shockwave could be launched, rippling outwards and producing that telltale, milliseconds-long flash of radio waves as its final, brilliant signature. Then there is nothing left. The system has been completely obliterated, either forming a single, more massive neutron star that almost immediately collapses, or creating a black hole outright. This is a one-time performance because the actors are gone. Another possibility is the death of a supermassive star, a behemoth far larger than our Sun. Its core, no longer able to support its own immense weight, catastrophically implodes. This is not a standard supernova. It is a direct collapse into a black hole, a process so violently efficient that it could channel a titanic jet of energy. powering a solitary fast radio burst as the star's last will and testament. The appeal of these cataclysmic models is their elegant finality. They naturally explain the silence that follows the flash. Supporting this grim picture, there have been tantalizing, though not yet conclusive, hints. Some one-off FRBs have occurred around the same time and in the same general patch of sky as detections of gravitational waves, the ripples in spacetime caused by massive collisions. While a definitive link is still elusive, it points toward a universe filled with these violent final acts. Each one-off burst may be the death rattle of a stellar system, a brief but powerful signal marking the end of a cosmic era and the birth of something new and dark. The sheer power of these cosmic flashes, concentrated into a mere instant, inevitably sparks a profound and tantalizing question. Could they be the work of intelligence? The idea is not just science fiction. Prominent theorists like Harvard's Avi Loeb have proposed a startling possibility. What if we are not witnessing a natural cosmic explosion, but the leakage from an immense alien engineering project? Imagine a civilization so advanced it builds interstellar light sails. To propel these vast sails across the gulfs between stars, they would need a powerful energy source, a focused beam of radiation. From our distant, accidental viewpoint, that tightly focused beam would appear as nothing more than a blinding, milliseconds-long flash as it swept across our solar system. It is a captivating vision, turning the cosmos from a realm of random cataclysms into a neighborhood of active, technological beings. Yet, for all its imaginative appeal, this hypothesis faces immense scientific hurdles. The energy required to send such a signal across billions of light-years is almost beyond comprehension, even for a hypothetical super-civilization. More critically, the very nature of the signals argues against a deliberate message. These bursts are not a finely tuned radio broadcast on a narrow, efficient frequency. They are messy, sprawling across a wide band of the radio spectrum, much more like the signature of a raw, natural explosion than a crafted communique. The existence of repeaters presents an even greater challenge to the idea of a directed signal. Why would an advanced species engage in such a sustained, astronomically wasteful effort, firing blast after blast into the void from the same location for years on end? It would be like shouting into a canyon with all your might, over and over, with no clear reason. The scientific consensus, therefore, rests firmly on the side of natural, if extreme, astrophysics. The extraterrestrial intelligence theory remains a fascinating thought experiment, a mirror that reflects our own deepest hopes and curiosities about the universe. It pushes us to think bigger, but it has not yet moved from captivating speculation into the realm of testable science. The real engines, it seems, are out there in the dark, natural, and waiting to be understood. Detecting these cosmic whispers requires an entirely new kind of ear, a global network of colossal radio dishes listening for a momentary blip in a sea of static. These telescopes are not like optical telescopes that see points of light. They are vast metal bowls, some as large as a football field, designed to catch the faintest ripples of radio energy from the cosmos. Their immense size is not for magnification, but for collection. They act like giant buckets in a rainstorm, gathering as many of those precious, weakened photons as possible from the burst that began its journey billions of years ago. The challenge is not just collecting the signal, but finding it within an ocean of data. These instruments scan the sky continuously, generating terabytes of information every single day, a digital deluge where the signature of an FRB is hidden as a subtle, descending chirp. To find it, sophisticated computer algorithms sift through this river of data in real time, searching for that unique fingerprint of dispersion. When they find a candidate, an alert can go out to astronomers around the world in mere seconds. This is where telescopes like CHIME in Canada change the game. Instead of a single, focused dish, CHIME is a stationary array of cylindrical reflectors, giving it an incredibly wide field of view. It is like looking at the entire sky at once, allowing it to catch dozens of these fleeting bursts every month that would have been missed by older, more narrow-focused instruments. But knowing a burst happened is only half the battle. You need to know where it came from. This is the specialty of telescopes like a SKAP in Australia. Its design allows it to act like a cosmic triangulation machine, using multiple dishes to pinpoint the location of a burst with astonishing precision, often narrowing it down to a single host galaxy billions of light-years away. This precise localization is the crucial first step. The moment an FRB is pinpointed, an alert flashes across the global astronomical network. Optical telescopes, X-ray observatories in space, and even gamma-ray detectors swiftly turn their gaze to that tiny patch of sky. They are hunting for a counterpart, any flash of light or burst of high-energy radiation that occurred at the exact same moment as the radio burst. Finding such a counterpart would be the ultimate breakthrough, a simultaneous signal that would instantly reveal the true nature of the cosmic engine. This global, collaborative hunt, powered by ever-improving technology, is transforming a trickle of mysterious events into a flood of data. With thousands of bursts now catalogued, patterns are beginning to emerge from the noise, giving scientists the statistical power they need to finally separate one cosmic cause from another. We are no longer just waiting for random flashes in the dark. We are actively listening to the universe, and it is starting to answer. This dispersion measure is the key that unlocks the signal's journey. Every fast radio burst carries this encoded diary of its voyage, a simple number that tells a profound story of distance. The principle is beautifully straightforward. As the burst travels, its light pushes through a sparse sea of free electrons, the fundamental particles stripped from atoms that drift in the vast spaces between stars and galaxies. These electrons act like a subtle cosmic fog, slowing the radio waves down. But here is the crucial part: they do not slow all the light equally. The lower frequency waves, the deeper tones of the signal, are impeded more than the high-pitched ones. This creates that distinctive descending chirp, where the high notes arrive at our telescopes a fraction of a second before the low notes. The greater the delay between the highest and lowest frequencies, the higher the dispersion measure, and the more electrons the signal has plowed through on its way to us. Since we have a rough map of the average electron density in our own Milky Way and in the intergalactic void, we can use this total electron count to estimate the total distance traveled. It is like knowing how many raindrops have hit your car windshield and using that to estimate how far you have driven through a storm. A very high dispersion measure almost certainly means the burst did not originate in our galactic neighborhood. It points to a source that has traversed the immense gulf between galaxies, placing its home billions of light-years away. Of course, this cosmic ruler is not perfect. Dense pockets of ionized gas near the source or unexpected clouds within our own galaxy can add extra electrons to the count, potentially making a relatively nearby burst appear more distant. For the most remote signals, however, the vast, empty stretches of intergalactic space contribute the overwhelming majority of the dispersion. This slight imperfection does not diminish its power. It simply makes the interpretation more nuanced. Each dispersion measure we collect does more than just locate a burst. It measures the invisible. It tells us how much tenuous, ionized material exists along a specific billion light-year-long path through the cosmos. By gathering thousands of these measurements from different directions, We are slowly charting the distribution of the universe's normal matter, much of which is too diffused to see by any other means. Every flash is not just a mystery, it is a single data point illuminating the dark, filamentary structure of the cosmic web itself. Pinpointing the origin of a flash that lasts 5 milliseconds is a monumental challenge. A single, massive radio dish might tell you a burst happened, but its location could be uncertain by several degrees on the sky. That is a huge area, a cosmic search zone containing millions of potential host galaxies. It is like hearing a single, sharp crack of thunder and trying to figure out which specific leaf in a forest spanning the entire horizon was struck by lightning. The breakthrough in this cosmic triangulation comes from a different kind of telescope, an interferometer. Instead of one giant dish, these instruments use a coordinated array of many smaller antennas spread across the landscape. By combining the signals from all these separate dishes, they mimic the resolving power of a single telescope as wide as the entire array. This technique provides an astronomically sharper view. When an interferometer like the Very Large Array in New Mexico or Australia's ASKAP catches a fast radio burst in real time, the result is transformative. It can pinpoint the burst's location not to a blurry, degree-wide patch, but to a tiny region of the sky measured in arcseconds. This is like moving from identifying the correct forest to identifying the exact tree. In many cases, this precision is so great that astronomers can immediately identify the specific galaxy that sent the signal, even from billions of light-years away. This precise localization is the crucial gateway to deeper understanding. The moment a host galaxy is identified, the real detective work begins. Optical telescopes like the Hubble Space Telescope or the Keck Observatories swiftly turn their gaze to that tiny point of light. They analyze the galaxy's color, its shape, and its light to determine what kind of cosmic environment produced such a violent event. Is it a massive, orderly spiral galaxy like our Milky Way, or a small, chaotic dwarf galaxy blazing with the birth of new stars? Is it old and metal-rich or young and primitive? Each of these properties acts as a vital clue. The discovery that many repeating FRBs originate in turbulent, dwarf galaxies with high rates of star formation, for example, strongly supports the Magnetar theory, as these are the very places where young, massive stars live fast, die young, and leave behind such magnetically charged corpses. The ongoing, relentless effort to localize more and more bursts, especially the elusive one-off events, is one of the most active fronts in this research. Every new galaxy identified adds another piece to the statistical puzzle, helping us see the patterns that connect these brilliant, fleeting flashes to the lives and deaths of galaxies across the cosmos. The home of the first repeating burst was not what anyone expected. When astronomers finally pinpointed the origin of FRB 1211-2, they found it not in a grand spiral like our Milky Way, but in a small, turbulent dwarf galaxy 3 billion light-years away. This was a crucial piece of the puzzle. This particular galaxy is a cosmic nursery, a place blazing with the furious birth of new stars. It is also what astronomers call metal poor, meaning it contains very few elements heavier than hydrogen and helium. These are the pristine, chaotic conditions where the most massive stars are born. They live fast, burn bright, and die young in spectacular supernova explosions, leaving behind dense, magnetized corpses like Magnetars. The environment itself was pointing directly to the source, but the clues did not stop there. The repeating bursts were traced to a specific, violent neighborhood within this galaxy, a region of intense star formation. And right next to the source of the flashes, astronomers found something else, a persistent, compact glow of radio emission. This steady beacon could be a magnetized nebula, a cloud of particles energized by the young, hyperactive magnetar at its heart, a constant reminder of the fury contained within. The entire picture, from the dwarf galaxy to the stellar nursery to the glowing nebula, fits the Magnetar model perfectly. It tells a coherent story of a young, monstrously magnetic neutron star, born from the death of a massive star in a primitive galaxy, throwing its violent tantrums across the cosmos. This single localization provided a Rosetta Stone for the entire field. It gave scientists a template, a specific type of galactic environment to associate with these mysterious signals. Now, when a new FRB is found, one of the first questions is, does its home galaxy look like the home of 1211-2? The answer is increasingly yes, at least for the repeating burst. This pattern strongly suggests we are not hearing from the quiet, elderly regions of galaxies, but from their most vibrant and violent stellar cradles, where cosmic monsters are born. The sheer power packed into that 5-millisecond flash is almost impossible to grasp. To understand the scale, picture our Sun, a continuous, stable nuclear furnace. Now imagine capturing its entire energy output, not for a second, but for days, months, or even an entire year, and then releasing it all in a single, instantaneous burst of radio waves. That is the staggering energy of a single fast radio burst, concentrated into a span of time shorter than a human heartbeat. This is not a gentle release of power. It is a cosmic detonation of unimaginable efficiency. For an object to do this, it must be able to store a colossal amount of energy and then unleash it all at once in a perfectly coordinated way. The emission itself holds another vital clue, its coherence. This means the radio waves are all marching in lockstep, like a perfectly synchronized laser beam, rather than the chaotic, random light from a light bulb. This organized, disciplined nature of the signal suggests an emission process that is fundamentally different from a simple explosion. It points to something like a natural cosmic maser, where conditions are just right to amplify radio waves into a powerful, coherent shout. So what natural engines could possibly meet these two extreme requirements: immense power and perfect coordination? The leading candidates all involve the most extreme objects in the universe, neutron stars and black holes, and their immensely powerful magnetic fields. One key idea is magnetic reconnection. Imagine the magnetic field lines around a magnetar trillions of times stronger than Earth's, becoming twisted and tangled beyond their breaking point. Suddenly, these lines snap and violently reconnect, a process that converts unimaginable magnetic energy directly into radiation and particle acceleration in a fraction of a second. It is an astronomical short circuit of cosmic proportions. Alternatively, the collapse of a supermassive star directly into a black hole could channel the gravitational energy of an entire star into a focused jet, powering the burst as the star winks out of existence. These are the few physical processes violent enough and fast enough to cross the immense energy threshold. The energy problem is not just a curious detail. It is the ultimate constraint, a set of physical rules that any viable theory must obey. It forces us to look at the most volatile, energetic corners of the cosmos, pushing our understanding of physics to its very limits in the search for an answer. The search for a single, simple answer is leading us into a cosmic zoo of theoretical monsters. Beyond the established suspects of magnetars and stellar mergers, astronomers are exploring a whole menagerie of potential sources, each one more exotic than the last. Consider the final moments of a supermassive neutron star. This is an object already on the very brink of existence, so dense that a single spoonful would weigh as much as a mountain. If it were to gain just a little more mass, perhaps from accreting material from a companion star, it could cross a critical threshold. In that instant, its own immense gravity would win, and it would catastrophically implode, vanishing inside a new black hole. This sudden disappearance, the literal collapse of a star into nothingness, could unleash one last coordinated scream of radiation, a fast radio burst marking the moment a star became a ghost. Then there is a scenario of pure cosmic violence on a smaller scale. Imagine a solitary neutron star, a dead sun wandering the galaxy. A comet or a large asteroid, perhaps a remnant from a shattered planetary system, drifts too close. The neutron star's gravity is so intense that it shreds the object into a stream of vaporized plasma even before it hits the surface. This cloud of superheated gas, swirling in the star's powerful magnetic field, could then act like a temporary radio transmitter, flashing brightly as it is torn apart. We might be hearing the death cries of asteroids falling onto dead stars. The theories become even more speculative, venturing into the realm of cosmic defects. Some physicists propose the existence of cosmic strings, unimaginably dense, one-dimensional cracks in the fabric of spacetime left over from the Big Bang. If these hypothetical strings truly exist and one were to snap or vibrate violently, it could release a titanic burst of energy, potentially explaining the most powerful one-off bursts we see. This dizzying diversity of ideas is not a sign of confusion, but a direct response to the data. The fast radio bursts we detect are not all the same. They come with wildly different energies. Some repeat in predictable patterns, others are completely random, and some have highly organized magnetic fields while others are messy. It is becoming clear that the term fast radio burst is likely an umbrella term, a single name we use for what are probably several different cosmic events that just happen to look similar from 3 billion light-years away. The universe is not using one engine but many. Our challenge is to listen closely enough to tell them apart. The radio waves themselves carry another hidden signature, a subtle alignment that speaks of powerful magnetic fields. Many fast radio bursts are strongly polarized, meaning their light waves do not just vibrate randomly in all directions. Instead, they oscillate in a single, preferred plane, like a crowd doing the wave in a stadium rather than a chaotic mosh pit. This polarization is a powerful diagnostic tool, a direct line into the magnetic environment the signal has traveled through. The most telling clue comes from a phenomenon called Faraday rotation. As a polarized radio wave passes through a cloud of magnetized plasma, its angle of polarization slowly twists like a screw turning. The more intense the magnetic field and the denser the plasma, the greater the twist. By measuring this rotation, astronomers can effectively weigh the magnetic strength of the material surrounding the source. For the famous repeater FRB 1211-2, the Faraday rotation was off the charts. It was not only incredibly high, indicating an immensely powerful magnetic field, but it also changed over time, increasing and then decreasing between bursts. This variability is the smoking gun. It points to a dynamic, turbulent environment, a nebula of hot, magnetized gas that is constantly churning and shifting. This fits perfectly with the picture of a young, active magnetar, blasting out flares that inflate its own persistent, energetic bubble. The polarization data gives us an independent line of evidence, separate from the burst's raw power or its repetition pattern. It allows us to probe the local conditions right at the source, as if we were sampling the air in the room where the explosion happened. Each new polarized burst adds another data point, helping us to map the invisible magnetic fields that weave through the distant universe. We are not just hearing the cosmic shout, we are now feeling the magnetic texture of the space from which it came. This stationary array in the Canadian wilderness sees the sky differently. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is not a single steering dish but a series of 4 massive stationary half-pipes, each as long as a city block. With no moving parts, it simply stares at the sky as the Earth turns, acting as a cosmic sieve that sifts through the entire northern hemisphere every single day. Its field of view is staggering, about 200 times the area of the full moon, all observed at once. This design makes it the perfect hunter for fleeting, unpredictable events like fast radio bursts. Where a traditional telescope might catch one burst by luck after years of searching, CHIME began catching them by the dozen, then by the 100. It unleashed an avalanche of new data, transforming the field from a study of rare anomalies into a robust statistical science. Suddenly, astronomers were not just collecting mysterious flashes, they were building a census. This flood of new detections revealed a stunning truth. Fast radio bursts are not rare cosmic jewels, they are common, everyday events in our universe. The best estimates now suggest that somewhere in the observable sky, a flash goes off not just once a day, but thousands of times. The cosmos is crackling with this invisible energy, a constant, silent fireworks display we were almost entirely deaf to. CHIME's vast sample size also revealed an incredible diversity. Some bursts have such low dispersion measures they might originate from within our own galactic neighborhood, hinting at quieter, closer sources we never knew existed. Others show breathtaking complexity in their millisecond profiles, with multiple peaks and dips suggesting a structured, repeating emission process happening within that tiny flash. This is no longer a search for a single answer. With a population numbering in the hundreds, scientists can finally begin to classify these bursts, sorting them into families based on their duration, their energy, and the structure of their signals. They can ask powerful new questions. Do bursts from certain types of galaxies share a common energy profile? Are the one-offs fundamentally different from the repeaters in more ways than just their silence? The CHIME Revolution has given us the first real map of this hidden territory, revealing not just the landmarks, but the vast, unexplored continent they are a part of. This faint, stretched chirp is more than just a mystery. It is a precise scientific instrument. Each fast radio burst acts as a cosmic backlight, a brilliant flashbulb that illuminates the vast, empty expanses between galaxies. As the signal journeys for billions of years, it passes through the intergalactic medium, the incredibly sparse and hot gas that fills the cosmic web. This gas is so thin, with just a few atoms per cubic meter, that it is completely invisible to traditional telescopes, but the radio burst feels its presence. Every single free electron in that gas leaves a tiny mark on the signal, slowing it down just a fraction and contributing to that all-important dispersion measure. Think of it like driving through a thick fog at night with your high beams on. You cannot see the fog itself, but you can see how its moisture dims and scatters your headlights. The greater the dimming, the thicker the fog you have driven through. In exactly the same way, the dispersion measure of an FRB tells us the total number of electrons it has encountered, giving us a direct, integrated measure of all the normal matter along its path. This is profoundly important. For decades, cosmologists have faced a puzzle. When they add up all the visible matter in stars and galaxies, a huge amount of the universe's ordinary atoms, its baryonic matter, seems to be missing. The leading suspect for this missing matter has always been a diffuse, hot gas spread throughout the cosmic voids. Fast radio bursts are now confirming this. They are directly weighing that invisible, intergalactic plasma, and the numbers are adding up. They are finding the missing atoms, but the power of this tool does not stop with a single measurement. By collecting dispersion measures from hundreds of bursts, each one originating from a different galaxy at a different distance, astronomers can begin to build a three-dimensional map of the universe's matter distribution. A burst from 5 billion light-years away gives us the electron count along a 5 billion light-year long path. A burst from 3 billion light-years away gives us a different path. With enough of these paths crisscrossing the cosmos, we can triangulate the invisible. We can see where the cosmic web is dense with filaments of gas and where the voids are truly empty. This allows us to test our most fundamental models of how the universe's large-scale structure formed from the faint ripples of the Big Bang. So every time one of these brilliant flashes is detected, it serves a dual purpose. It brings us closer to understanding its own violent origin, and simultaneously, it illuminates the dark, filamentary skeleton of the cosmos itself. A brilliant radio flash is only half the story. To truly understand these cosmic explosions, we need to see them in a different light, literally. The most urgent goal in this field is to catch a fast radio burst in the act across multiple channels, to find a second, simultaneous signal from the same patch of sky. This is the dream of multi-messenger astronomy, and it would be the ultimate smoking gun. Imagine if the moment a radio telescope recorded a burst, an orbiting gamma-ray observatory also saw a flash from that exact location. That single coincidence would instantly validate one of our leading theories. A simultaneous short gamma-ray burst, for example, would be a near-certain sign of a neutron-star merger, the final, violent collision of two dead stars. Alternatively, a detection from a neutrino observatory, capturing a ghostly particle from the heart of the cataclysm, would point directly to the intense, dense processes at work inside a newborn magnetar. This is the power of a multi-messenger approach. It uses different senses to build a complete picture of a single event. To make this happen, the world's observatories operate a sophisticated alert system. The instant a radio telescope like CHIME or a SKAP pinpoints a burst, an automated notice flashes across global networks. Within seconds, robotic optical telescopes swivel to stare at the source. Space-based observatories like SWIFT and Fermi, designed to catch gamma rays, check their data for any corresponding flash. Even gravitational wave detectors like LIGO and Virgo can scan their records, searching for a ripple in spacetime that arrived at the exact same moment as the radio wave. The entire astronomical community holds its breath, hoping for a correlation. So far, the results have been teasingly ambiguous. A few potential associations have been noted: a flicker of gamma rays here, a possible gravitational wave there, but nothing has been repeated with the high confidence needed for a definitive claim. The chase continues, a testament to the collaborative spirit of modern science, where experts in gravity, particles, and light unite to solve a mystery that no single field can crack alone. The repeating signals defied the finality of a cosmic explosion. If the source was destroyed in a single, brilliant flash, how could it possibly speak again months or even years later? This fundamental contradiction forced scientists to abandon the idea that all fast radio bursts were death cries. The repeaters pointed to an engine that could survive its own violent outbursts. The prime suspect became the young, active Magnetar. Think of this object not as a serene corpse, but as a volatile, spinning toddler of a star, full of pent-up energy and prone to tantrums. Its incredibly rigid crust is under constant stress from the unimaginably powerful magnetic field twisting within. Over time, this stress builds until the crust can no longer hold, fracturing in a starquake. This single event unleashes a shattering blast of magnetic energy, which we detect as 1 FRB, but the star itself remains. It simply begins the process again, building up stress until the next fracture occurs. This elegantly explains the sporadic nature of the repetition. It is not a scheduled event, but a release of seismic pressure, much like the unpredictable timing of earthquakes on our own planet. The environment around the Magnetar might also play a crucial role. If the star is swaddled in a dense nebula of its own making, a cloud of particles from previous outbursts, this material could act as a buffer or a modulator. It might absorb some of the energy from smaller cracks, preventing a detectable burst, and only allow the truly colossal ruptures to shine through. This would create periods of quiet followed by sudden, frantic activity. The patterns themselves are a cryptic code. Some repeaters have long dormant phases, staying silent for years before erupting in a flurry of bursts. Others fire off with a strange, almost predictable rhythm. Deciphering this code is essential. Are we seeing the same basic process playing out on different timescales, or are there multiple types of repeating engines? The answer could reveal that one-off bursts and repeaters are not different beasts at all. Perhaps every FRB source has the potential to repeat, given enough time and the right conditions. A one-off burst might simply be from a magnetar that has not yet built up the stress for a second major quake, or whose subsequent bursts were too faint for us to detect. Conversely, the single, immense flashes might still represent a distinct class of event, a true cataclysm that leaves no engine behind. The great divide between the one-time shout and the chattering repeater is the central mystery that could ultimately classify the entire zoo of these cosmic signals. The search for these cosmic flashes is now tuning into a different frequency, shifting from the familiar high notes to a deeper, rumbling bass. For years, most hunts concentrated on frequencies around 1 to 2 GHz, a relatively clean band where our technology excels. But the universe broadcasts across the entire radio spectrum, and a new frontier has opened at the lowest frequencies, below 300 MHz. Telescopes like the Low Frequency Array, or LOFAR, are pioneering this effort, catching bursts in a domain where radio waves behave very differently. At these deep tones, the cosmos is a far noisier and more obstructive place. Low-frequency radio waves are easily scattered and absorbed by the thin plasma that permeates space. They can be bent and blurred like a distant street lamp seen through a foggy window. For a fast radio burst to punch through this haze and still be detected on Earth, its initial blast must be phenomenally powerful, far brighter than we ever assumed. This simple fact of detection is a powerful filter. It tells us that the bursts we see at low frequencies are coming from the most energetic engines in the cosmic zoo. How a signal behaves across different frequencies acts as a diagnostic tool for its origin. Some theoretical models for magnetar flares predict they should be brilliant emitters at low frequencies, while the shock waves from stellar mergers might be suppressed or absent. By comparing the high-frequency and low-frequency portraits of the same burst, we can start to rule out entire classes of theories. The low-frequency window also sharpens our most fundamental measurement, the dispersion measure. The stretching of the signal, that descending chirp, is far more pronounced at the deepest radio tones. This gives us an exquisitely precise reading of the total number of electrons the burst has encountered on its journey, refining our cosmic map of the unseen material between galaxies. Every low-frequency detection is a double revelation, telling us about the burst's own violent nature and clarifying the structure of the cosmic web it passed through. As we expand our hearing into this new realm, we may soon discover entirely new categories of bursts, whispers from the dark that were simply too deep for us to hear before. But what if the sheer power of these flashes is an illusion? The staggering energy we calculate for fast radio bursts relies on one critical assumption. that the signal we receive is the same brightness as when it left its source. Yet there is a fascinating cosmic trick that could be distorting our view, a phenomenon known as plasma lensing. Imagine a dense, invisible cloud of ionized gas floating in the space between the burst and us. As the radio waves pass through this cloud, they bend, much like light bending through a glass lens. In the right conditions, this plasma can act as a natural cosmic magnifying glass, focusing the radio waves and making a relatively faint burst appear spectacularly, deceptively bright from our vantage point. This lensing effect would not just amplify the signal, it could also split it. A single burst could be duplicated, its waves taking slightly different paths around the plasma cloud, creating multiple images that arrive at our telescopes microseconds apart. This could explain some of the incredibly complex, multi-peaked structures we see within a single flash, patterns we might otherwise attribute to a convoluted explosion process. If plasma lensing is a common occurrence, it fundamentally changes the energy budget. The most brilliant bursts might not require an engine of almost impossible power. Instead, their apparent brilliance could be a mirage, a trick of cosmic optics that makes a merely powerful event look truly apocalyptic. This would bring the energy requirements down to a more manageable scale, making existing models like Magnetar flares far more feasible. The hunt is now on for the unique fingerprint of lensing. Astronomers are searching for specific patterns in how the amplification changes with frequency, a telltale signature that the burst has been artificially enhanced on its journey. Finding this signature would be a monumental step, not just solving an energy puzzle, but revealing a new layer of complexity in the interstellar medium of distant galaxies. It forces us to ask a humbling question. Are we witnessing the raw power of cosmic monsters, or are we simply seeing their faint whispers magnified by ghostly lenses in the dark? That faint chirp is a cosmic scale. For decades, cosmologists faced a deeply unsettling accounting problem. When they tallied all the normal matter in the nearby universe, the stars and galaxies and gas clouds we can see, the numbers did not add up. Over half of the atoms predicted to exist from the Big Bang were simply missing. This was the missing baryon problem, a glaring hole in our understanding of the universe's basic inventory. The prime suspect was a ghostly, diffuse gas known as the warm-hot intergalactic medium, or WIM. Theorized to be a web of incredibly thin, million-degree plasma stretching between galaxies, it was simply too faint and too spread out for any telescope to see directly. We knew it had to be there, but we had no way to prove it. This is where the fast radio burst becomes more than a mystery. It becomes a precision instrument. Each burst's dispersion measure is a direct tally of every free electron it has encountered on its billion light-year journey. The vast majority of those electrons are not in galaxies, but in the invisible WIM that fills the cosmic voids. By collecting the dispersion measures from many bursts, each one originating from a galaxy at a known distance, astronomers can finally weigh this elusive material. It is like trying to measure the density of a fog by seeing how much it dims the headlights of cars coming from different distances. A car from a mile away gives you one measurement. A car from 5 miles away gives you a longer path through the fog. With enough cars, you can map the fog's entire distribution. Early results from surveys like CHIME are already bearing fruit. The total amount of matter inferred from hundreds of FRB dispersion measures is aligning almost perfectly with the predictions from the Big Bang. The missing atoms are not missing at all. They have been hiding in plain sight, woven into the fabric of the cosmic web. In solving their own mystery, these brilliant flashes are illuminating the dark corners of the universe, transforming from cosmic anomalies into essential tools for fundamental cosmology. With hundreds of these cosmic flashes now catalogued, a new picture is emerging from the noise. We are no longer just chasing ghosts, we are taking a census of the entire population. The statistical portrait reveals that fast radio bursts are not a single, monolithic phenomenon. Their properties, from their raw energy to their duration, span a vast continuum. Some bursts are barely a whisper, while others are true cosmic shouts, a range of power spanning a factor of 10 million. This distribution of energy follows a specific mathematical pattern known as a power law. It is the same pattern we see in earthquakes, where small tremors are common and massive quakes are rare, or in solar flares, where tiny flickers far outnumber colossal eruptions. This scale invariance is a profound clue. It suggests the underlying physics, the engine behind these bursts, operates in a similar way regardless of the event's size. A single physical process, like a magnetic starquake on a magnetar, could produce a small ripple or a catastrophic rupture, naturally explaining why we see so many weak bursts for every extraordinarily powerful one. The bursts are also scattered evenly across the entire sky. They come from every direction, a distribution astronomers call isotropic. This tells us that fast radio bursts are not a local oddity, not something emanating from a particular structure in our cosmic neighborhood. Instead, they are a universal phenomenon, a fundamental part of how the cosmos behaves in galaxies far and wide. This even spread implies that the conditions needed to create these flashes are common, happening in all types of galaxies across the observable universe. The most telling statistical split remains the great divide between the one-off bursts and the repeaters. The data increasingly suggests these may be two distinct families. The one-offs tend to be, on average, more energetic, the true cosmic blasts that scream and then fall silent forever. The repeaters are often slightly less energetic but far more talkative. This dichotomy points to two different kinds of cosmic engines, one that destroys itself in a final, brilliant act, and another that endures to flare again and again. As our sample size grows from hundreds into the thousands, these statistical studies will become incredibly powerful. We will be able to ask sharper questions. Do bursts from spiral galaxies have different energies than those from dwarf galaxies? Is there a specific age or metal content that makes a galaxy more likely to host a repeater? By correlating the properties of the flash with the properties of its home, we can begin to build a unified theory, a classification system that finally makes sense of the entire cosmic zoo. Every new detection is no longer just a mystery. It is another day to point on a graph that is slowly revealing the true nature of these brilliant, fleeting events. Every flash we detect is a victory against an ocean of noise. A telescope like CHIME does not just listen to the sky, it is inundated by it, generating a torrent of digital information equivalent to the entire printed collection of a major library every single second. Within that roaring river of data, the faint, descending chirp of a fast radio burst is a whisper easily drowned out. The interference is relentless, a constant static of human origin. Passing satellites broadcast their status, cell phone towers hum with activity, and even a microwave oven in the observatory's break room can create a spike that mimics a cosmic event. Separating the celestial signal from this terrestrial cacophony is the first and most critical battle. This is where sophisticated algorithms, many of them powered by advanced machine learning, take over. These are not simple filters. They are digital sleuths trained to recognize the unique fingerprint of dispersion, that subtle stretching of the signal that speaks of a billion light-year journey. They scan the data in real time, flagging only the most promising candidates amidst the chaos. But the machine's work is only the beginning. each candidate must pass under the eyes of human experts, astronomers who make the final judgment call, distinguishing a true cosmic event from a clever mimic. The clock is always ticking. Once a burst is confirmed, an automated alert must race across the globe within seconds. Optical telescopes, gamma-ray observatories, and gravitational wave detectors need that immediate notification to swing into action, to capture any fleeting glow or ripple that might accompany the radio flash. This global, coordinated response is a technological ballet, a seamless handoff from silicon to human to a worldwide network of instruments. The real breakthrough is not just in building bigger dishes, but in crafting the digital brains that can process this cosmic fire hose of information. It is a silent, ongoing revolution in computing and data science that is unlocking the universe's faintest, fastest secrets. The hunt for these cosmic whispers is about to leap into a new era of discovery. On the horizon are observatories of such sensitivity they will hear the faintest echoes from the dawn of time. The crown jewel is the Square Kilometre Array, or SCAR, a monumental project slated for the 2030s. This will not be a single telescope, but a vast network of thousands of dishes and antennas spread across 2 continents, in South Africa and Australia. Together, they will create a collective listening area of, as the name implies, 1 square kilometer, making it the most sensitive radio telescope ever conceived. Its power to detect fast radio bursts will be staggering. It will catch signals from the very edge of the observable universe, flashes that began their journey when the universe was in its infancy. More than just detection, the SKA's incredible resolution will pinpoint a burst's origin not just to its host galaxy, but to a specific stellar neighborhood within it, allowing us to see the exact environment where these explosions are born. While we await the SKA's revolution, a new generation of hunters is already coming online. In the United States, the Deep Synoptic Array, or DSA, has begun its search. With its 210 carefully designed radio dishes, it is engineered for one purpose: to find and precisely locate dozens of fast radio bursts every single year. Each localization is another piece of the puzzle, another galaxy added to our growing map of where these events occur. The data from these future instruments will be exquisitely rich. We will not just know that a burst happened, we will see its polarization in fine detail, tracing the twists of its magnetic journey. We will dissect its spectral structure, understanding how its energy is distributed across different radio frequencies. We will analyze its millisecond profile with a clarity that reveals the inner workings of the explosion itself. This flood of high-quality information will finally allow us to achieve the field's ultimate goals. We will solve the progenitor mystery, conclusively linking specific burst signatures to their cosmic engines, whether they are magnetars, mergers, or something entirely new. We will create a definitive classification system, sorting the cosmic zoo into distinct families, and we will fully harness their power as tools for cosmology, using thousands of these cosmic flashbulbs to map the dark, invisible matter of the universe with breathtaking precision. The next decade promises to transform these enigmatic flashes from profound mysteries into fundamental keys for understanding the cosmos. The discovery of fast radio bursts feels like a modern mystery, but the universe has likely been broadcasting them for eons. Why did we only begin to hear them in the 21st century, after decades of operating radio telescopes? This timing raises a profound, almost philosophical question about our place in the cosmos. It touches on what is known as the Anthropic principle, the idea that our observations of the universe are unavoidably filtered through our own existence and capabilities. We do not see a random, objective cosmos. We see the universe that we are equipped to see. there is no reason to believe these brilliant flashes are a new celestial event, a sudden cosmic fashion that began just as we learned to listen. They have almost certainly been occurring for billions of years, a constant, invisible fireworks display throughout cosmic history. Our present epoch is unique for one simple reason. It is the first time a civilization on Earth has developed the technological sophistication to capture these millisecond whispers. It is a matter of perfect timing between the development of our digital ears and the universe's endless performance. This realization is deeply humbling. It frames our entire scientific journey not as a final unveiling of truth, but as a gradual lifting of veils, each one dependent on the tools we invent. The history of astronomy is a story of these lifted veils, from Galileo's first telescope revealing the moons of Jupiter to the modern arrays that now catch cosmic chirps from billions of light years away. What we perceive as the universe's character is, in many ways, a reflection of our own technological maturity. This perspective suggests an exhilarating future. If a mystery as profound as fast radio bursts could remain hidden until now, what other cosmic phenomena are currently invisible to us, simply because we haven't yet built the right instrument to perceive them? The cosmos is likely filled with wonders we cannot yet even imagine, waiting for the next generation of listeners to finally tune in. These ghostly signals have escaped the world of academic papers to become modern cosmic legends. You can find fast radio bursts featured in major news headlines, woven into the plots of science fiction novels, and showcased in television documentaries. Their appeal is undeniable, a perfect storm of mystery and power. They are cosmic enigmas wrapped in a simple, tantalizing question: what is out there? This question resonates with a fundamental human curiosity, a deep-seated wonder about our place in the universe and the possibility of other intelligences. When a scientist announces the detection of a new repeating burst from a distant galaxy, it is not just a data point, it is a story. The public imagination naturally leaps to the most thrilling possibilities, envisioning alien messages and cosmic engineering on an unimaginable scale. This widespread fascination is a tremendous force for good in science. It translates into public support for building bigger telescopes and funding ambitious research missions. It inspires a new generation of students to look up at the night sky and dream of becoming the astronomers who will solve these mysteries. Yet this very excitement also carries a weighty responsibility for the scientific community. Researchers must walk a delicate line, nurturing that sense of wonder while carefully separating the established facts from the captivating speculation. They must clarify that while an extraterrestrial intelligence is a fun thought experiment, the evidence overwhelmingly points to natural, if extreme, astrophysical events. This dance between inspiration and accuracy is crucial. The story of fast radio bursts demonstrates how the most profound scientific quests can capture our collective imagination. It builds a bridge between the complex mathematics of plasma physics and the simple, universal human urge to explore the unknown. In the end, these brief flashes do more than illuminate the cosmic web. They light a fire of curiosity that burns in all of us. The universe, it seems, refuses to give up its secrets easily. For every answer we uncover about fast radio bursts, a dozen new, more intricate questions emerge from the cosmic static. We have identified likely suspects and powerful engines, yet the most fundamental mysteries remain stubbornly unresolved. Perhaps the most glaring gap in our understanding is the true identity of the one-off bursts. We have compelling theories like neutron star mergers or collapsing stellar cores, but a definitive progenitor remains elusive. These solitary flashes offer no second chance for study. They are cosmic ghost stories, whispered once and then swallowed by an eternal silence. So are the repeaters and the one-offs fundamentally different phenomena, born from two separate classes of cosmic catastrophe. Or are we simply seeing different stages or different expressions of the same underlying engine, where a repeater is a young, active magnetar, and a one-off is an older one finally tearing itself apart in a final, fatal quake? The data is not yet conclusive, leaving this great divide as the central, unresolved schism in the field. Even the behavior of the known repeaters is deeply puzzling. Why do they have such erratic personalities? A single source might fire off a frantic volley of dozens of bursts in a single hour, only to fall completely silent for months or even years. This sporadic activity suggests that the engine is not running on a simple, predictable clock. It could be building up stress slowly, like tectonic plates before a massive earthquake, only releasing its energy in a sudden, catastrophic rupture. Or perhaps a dense shroud of plasma and debris sometimes surrounds the source, absorbing smaller bursts and only allowing the most powerful eruptions to punch through. The complex internal structure of the bursts themselves adds another layer of mystery. Some signals are not clean, simple pulses. They show intricate substructure with multiple peaks and dips all packed into a few milliseconds. This is not the signature of a single, simple explosion. It suggests a far more organized and sequential process, like a series of shock waves echoing through a magnetized nebula, or the rapid-fire eruption of multiple independent flares from the surface of a hyperactive neutron star. Decoding this millisecond symphony is key to understanding the precise mechanics of the emission. The hunt for a smoking gun counterpart continues with relentless urgency. The dream is to catch a fast radio burst at the exact same moment that a gravitational wave observatory feels a ripple in spacetime from a neutron star merger, or a neutrino detector catches a ghostly particle from a collapsing stellar core. Such a multi-messenger detection would instantly validate one of our theories, moving it from compelling speculation to established fact. So far, this definitive correlation has remained just out of reach, a tantalizing possibility that drives the global coordination of telescopes every time a new alert comes in. And then there is the most profound, lingering question of all. Are we absolutely certain that every single one of these signals has a natural origin? The scientific consensus is a firm yes, but the sheer power and strangeness of these events mean the door must remain, if only slightly, ajar for more exotic explanations. While the alien megastructure hypothesis has faded due to the natural-looking properties of the signals, it serves as a crucial reminder of how little we truly know about the extremes of cosmic physics. These open questions are not a sign of failure. They are the very engine of scientific discovery. Each mystery motivates the construction of more powerful telescopes, the development of more sensitive detectors, and the creation of more sophisticated theoretical models. The story of fast radio bursts is far from over. It is a living, breathing field of science where every new detection has the potential to overturn our assumptions and reveal a deeper, more complex universe than we ever imagined. The quest for a single, elegant theory to explain every fast radio burst is the grand prize in this cosmic puzzle. But the universe, in its infinite complexity, rarely offers such simple answers. The evidence points not toward one monolithic engine, but toward a diverse cosmic zoo of sources. Our unified theory, then, is less a single equation and more a detailed classification system, a field guide to the different types of brilliant flashes in the dark. One clear pathway is now well established, linking the chattering repeaters to the violent nursery of young magnetars. These stellar toddlers, born in the turbulent, metal-poor dwarf galaxies that blaze with new stars, are prone to frequent and dramatic magnetic tantrums, firing off burst after burst. Another, more final pathway seems to explain the solitary, one-off shouts. These appear tied to ancient, cataclysmic events within older, more settled stellar populations. The last scream of a system destroying itself in a neutron-star merger or a direct collapse into a black hole. This is not a sign of failure, but a sign of maturity in the field. We are learning to distinguish the cosmic chatterbox from the solitary screamer by the company they keep and the energy they release. The flood of new data from powerful surveys is the key that is unlocking this classification. With hundreds of bursts now catalogued, patterns are solidifying. We can ask powerful statistical questions. Do repeaters consistently have lower average energies than one-offs? Do their host galaxies always look a certain way? The answers are increasingly yes, allowing us to map specific observational signatures directly to their likely astrophysical engines. While a single, simple answer for every flash seems improbable, the scientific community is converging on a shortlist of viable models that can explain the vast majority of events. We are closer than ever to a comprehensive understanding, assembling the final pieces of a puzzle that reveals not one monster in the dark, but an entire menagerie of cosmic power. Our journey through these cosmic whispers reveals a universe both chaotic and beautifully structured. We began with a single, almost discarded signal, and have now entered an era where we catalog these events by the hundreds. Each flash, whether a repeater's chatter or a one-off's final cry, has forced us to rethink the limits of stellar life and death. These bursts are more than just puzzles. They have become precision instruments, weighing the invisible matter that binds the cosmos and mapping the vast, dark voids between galaxies. The collaboration of telescopes across the planet and in space, all working in unison to catch a flash, represents a new golden age of exploration. We stand on the brink of monumental discoveries with powerful new instruments like the Square Kilometre Array, poised to listen deeper into the universe's history than ever before. While the full story of fast radio bursts is not yet written, the progress is undeniable. What was once a single, baffling anomaly is now a rich field of science, teaching us not only about distant cataclysms but about the fundamental structure of reality itself. This enduring mystery is a testament to our own insatiable curiosity, a drive to understand the cosmos that compels us to build better tools and ask ever deeper questions. The universe continues to speak in these brilliant, fleeting shouts. Our task is to keep listening, to keep decoding, and to remain forever captivated by the unknown. Thank you for joining this exploration into one of astronomy's greatest modern enigmas. If you enjoyed this journey to the edge of our understanding, be sure to subscribe for more voyages into the mysteries of the cosmos.